Stick with that. Yes, that last semester had an early one.
Okay. So let's jump back into where we were on gravitational waves. And we were talking about this all in the context of deriving strains that are induced due to the passage of a gravitational wave, right? So the passage of a gravitational wave literally stretches and contracts space-time, inducing a strain, which we wrote down as, in the end, this sort of normalized strain as a function of time and space induced from some gravitational wave. We expressed r as the distance from the source to the observer in terms of the mass quadrupole moment of the matter distribution time in some retarded time t minus r as a function of time t minus r. And this is the second time derivative double dot of that quadrupole moment. And from this, we can define the reduced quadrupole moment. Just abbreviate there. And that's going to be squiggly ij, which is going to be our regular ij minus 1/3 the flat metric times the trace of I. So here I is IA, the trace of that quadrupole moment of I. And this whole thing is, it's really the traceless part, right? We've done this separation many times. Where we've taken off the trace from something and made a traceless part. We'll do that again when we go to the evolution equations on Thursday. Okay, so now we want to project this thing into the direction of propagation to understand how the strain is actually evolving, okay? So now the next step is to use a projection operator as following. This is going to be P, now covariant I, contravariant J, which we're going to define as eta ij, so mixed components of the flat metric, minus this normal vector, which in I is going to be equal to the coordinates xi over r, and this is the direction of propagation of the gravitational wave. Propagation of the gravitational wave. So that's not our normal vector like we think of in 3+1 where it's moving in the time direction. Specifically, this is the direction of propagation of the wave that we're dealing with. All right, and now we want to remove the transverse traceless part. From this. And so what we're going to do to remove the transverse traceless part of our reduced quadrupole moment is we'll have this ITT for transverse traceless, IJ, which we're going to define to be this projection operator IK, projection operator JL, minus 1/2 P downstairs IJ, P upstairs KL, all operating on our reduced quadrupole moment KL. And so that projects away that transverse traceless part. And gives me, well, the transverse traceless quadrupole, reduced quadrupole moment. So now I can then define a strain for this metric perturbation, right? Which we've already identified essentially as the strain. The transverse traceless part of that as a function of time and space is equal to 2 over the distance, this second time derivative of the transverse traceless reduced quadrupole moment ij as a function of the retarded time. Okay. And this is specifically, just to remind you where we started from last week, this is for the weak field limit. Also for the slow limit. Nothing's moving relativistically either. It's appropriate for that. As such, we've related the metric perturbation, h, directly to the quadrupole moment of the mass distribution. So this is also often called the quadrupole approximation. And bear in mind, this is an approximation. We have related this metric perturbation to the quadrupole moment of mass distribution. We've dropped higher order terms, and we've assumed that the gravitational field is weak and nothing's moving fast. And so this is approximate. But it works pretty well. Okay. So, make a real life application a little bit here. So let's say we've got color. Just to orient us with where we're at. So let's draw a little diagram here. Say X, Y, Z. And then let's say there's some point out here. Here is a source of gravitational waves. So that's some source. And then out here, we have some observer at some r, theta, phi coordinate in a spherical harmonic, or a spherical basis, right? Here we have observer, who's trying to measure the strain induced from some gravitational wave passing by. All right? So in this context, we have the 3 metric for this particular problem is dl squared is equal to dr squared plus 1 plus h plus r squared d theta squared plus 1 minus h plus sine squared theta d phi squared plus 2 times h plus sine theta d theta d phi. So that's from our metric that we wrote down before, where I'm putting in now the amplitudes of the 2 polarization state, well, just in this case, just the plus polarization state, because I can choose to do that. Okay? So in an orthonormal basis, in the basis, which we're used to here, of E r hat, E vector, theta hat, E vector, phi hat. Remember, our hats mean that it's orthonormal, right? And those are our basis vectors, and they are orthonormal. The polarization modes are got enough room for this. H plus is going to be equal to 1 over r, the distance to the source, curly I, double dot, in the theta hat direction, minus curly I, double dot, in the phi hat direction. And then H cross, even easier in this basis, is 1 over r, curly I, double dot, theta, phi hat, I mean. That's it.
There'd still be an r squared on the d phi squared term. The 1 minus h plus 1, or yeah, there should be an r on the, or an r squared on, or the 4th, maybe the last one.
I agree with you.
The last one should have r to the 4th, probably.
Let me see if I wrote that down.
Make the units. Oh, yeah, r squared on the last.
Are we?
Oh, they were still the squared one too.
So we're good?
No, the last 2 should have r.
Yeah, each of them.
The last 2 should have r squared, right?
Yeah.
No, I must have wrote this down wrong. Let me double check. You all right there? Yeah. Hold on. I must have copied it wrong. Working too quick. Just want to double check. Where is all this? There it is. So, I did not copy it incorrectly. If that is a mistake, it is a mistake in the book. But looking at it, I would have thought there should be an r squared there. Yeah. Because this is unitless, right? One is usually unitless. Correct. I really think you're right. I think there should be an r squared there.
Yeah.
I think that's the only way it makes sense.
You don't think it's like some geometrized units thing where there's a C missing or something? I'm just
The angle doesn't make any sense without knowing how far away you are in your origin,
Yeah.
as far as determining your distance.
And in every other case where we've had a metric like this, you've always got that r squared term there and the different components of the metric. So I think that just must be a mistake, in which case it's a mistake in the book. I actually been trolling around the internet today for the errata from the book. I know that they exist somewhere.
Yeah, I tried finding that because there's one of the problems should have or had a pretty sure it had a typo in it where it was like a tilde instead of a bar.
Mm-hmm.
I could not find.
Mm-hmm.
It was,
I swear I found it somewhere.
I think it was. Yeah, if you use their definition of like a tilde, your factors of sine disappeared or vice versa from a bar.
Pretty sure that's
And I spent a while looking for the errata, I couldn't find it.
Yeah. Okay, let's just go with there must be an r here. Okay. We can transform this to a Cartesian basis, which is useful. The expressions are a bit more involved. So now, of course, we're in our Cartesian basis, which you're all comfortable with. So h plus will now be, we still got the 1 over r out front, open bracket, curly I double dot x x minus curly I double dot y y all over 2 times 1 plus cosine squared theta times cosine of 2 phi plus curly I double dot xy all times 1 plus cosine squared theta times sine of 2 phi plus the quantity of curly I zz double dot minus curly I double dot xx plus curly I double dot yy all over 2 all times sine squared theta, close bracket. So a bit more complicated. Now, the significance here of the theta is sort of that angle from the direction of the wave in some sense. And so, Mike, this expression must look familiar to you because you take phi equals 0 and then we assume the equator. And this is essentially the formula that Mike has been using to compute gravitational waves from supernova simulations in 2D. For the plus polarization, there is no cross polarization in 2D. All right, cross polarization is 1 over r minus curly I double dot xx minus curly I double dot y all over 2 cosine theta sine of 2 phi plus curly I double dot xy cosine theta cosine of 2 phi, close bracket. No. Like that. So I didn't show the derivation of these, but you can kind of get at it trivially from the equations that we've already written down for how we express the polarization states in the quadrupole approximation. They follow immediately from that. Okay, and these are useful formula for the quadrupole approximation, and literally these are what we use in our simulations to extract gravitational wave information. It's an approximation, but it works pretty well, and these things are fairly easy to compute in a simulation. It's just the mass quadrupole moment, right? And so that's pretty easy to compute. Practically speaking, we often compute only the first derivative of the quadrupole moment. You can write down an analytic expression for that's easy to compute, and then you take the second derivative numerically, just with a finite difference. And that's what we often do in actual calculations. Now, if you want to get more sophisticated than the quadrupole approximation, the book has a couple of the main formalisms for directly extracting the gravitational wave information from a dynamic spacetime. I won't talk about those today because we just don't have the time. So I'm going to hit some of the highlights of that stuff. But in terms of what we do, this is it. Now, the gravitational waves carry energy and momentum as well as angular momentum, right? They cause perturbations in spacetime. Therefore, they represent some amount of energy. And to see this, let's write down in a Minkowski frame the stress energy of gravitational waves. So in a Minkowski frame, the stress energy of gravitational waves is going to look something like this. So TAB, gravitational wave, it's going to be 1 over 32 pi times the average over a few wavelengths of partial A of H transverse traceless Ij times partial B H transverse traceless upstairs Ij, where the average is taken over several wavelengths of the gravitational wave. Okay? That's what I mean by that. Okay, so then the outgoing, going away from the source, radial energy flux carried by the gravitational waves is then, just like we did before, it's the time and radial component of the stress energy tensor. We did that for matter, right? If you want to look at the energy flux for matter. Time component, radial component. So this is the energy flux in gravitational waves moving in the radial direction. All right? And from that, we can derive a gravitational wave luminosity. That's just energy per time. Luminosity. And that's going to involve an integral. And this luminosity in gravitational waves has got to be equal to the change in energy of the system due to the emission of gravitational waves. Well, minus the change in energy. Because the gravitational waves are carrying energy out of the system, the luminosity then is the negative, that energy loss rate. And that is computed via minus, take the limit of r going to infinity, so a distant observer, of the integral of our time radial component of the gravitational wave stress energy, r squared d omega. So integrate over solid angle, and then you can get that luminosity, right? So this is an integrated energy flux passing through some large sphere centered on the source of gravitational waves, right? That r goes to infinity. I'm taking the large sphere approximation because I want to be distant from the source in order for these equations to apply. But that's my luminosity in gravitational waves. We can write this down in terms of our polarization amplitudes in the gravitational waves. So now that I've pointed at them, I can erase them. Of course, this is Cartesian. So in terms of H plus and H cross, the gravitational wave luminosity, which is minus dE dt, is going to be minus the limit as r goes to infinity I don't have a minus sign on my notes, but I really think it must be there. I'll double check that in just one hot minute. The integral of the average of h dot squared plus h dot cross squared d omega. So the first time derivatives of these polarization amplitudes squared, added together, averaged over some sufficiently long period of time to take several wavelengths, and then angle averaged, integrated over the solid angle. Okay? Okay. And so in deriving this, sorry, my notes were cut off here, and so I can't quite read my writing. H transverse traceless ij, the spatial derivative, partial with respect to r, is equal to minus the time derivative of H transverse traceless ij for radiation that is moving out radially. So it's radiation, so it's moving at the speed of light, right? Or really we should say gravity here. And so I can interchange these derivatives by just using a minus sign for this particular case. And I use that there. And so this is equal to the energy that is lost in gravitational waves by the system. You know what? It very well could be. Let's double check, just to make sure it's not my mistake. Yeah, that's where the minus sign went. Okay, and so now we can take this a step further, and we can express this in terms of our reduced quadrupole moment as so in terms of the quadrupole moment, like we had before, the gravitational wave luminosity is, in that case, substituting in our expression for the quadrupole moment that we had up here before, and replacing that here becomes actually pretty easy. 1/5 the time average of curly I triple dot JK times curly I triple dot JK. So inner product averaged over some sufficient wavelength. Oh, 3 dots. 3 dots. And Mike, again, does that look familiar? You just computed this recently. Okay. All right. And just to remind you from last time, the reduced quadrupole moment, I guess I wrote this up just a minute ago. I can't remember, did I? Yeah, I did. Eta ij I. Yeah, I wrote that up. And the quadrupole moment, just for completeness sake for today, I, not curly, as a function of time, is defined as the integral over the volume of the rest mass, which is a function of time and space, should be a prime there, and multiplied by space again. So it's a second order moment. That's why there's 2 powers of the space coordinate there. Okay. So not only do gravitational waves carry energy, and so we can measure luminosity in gravitational waves, for systems with non-zero angular momentum, they also carry away angular momentum. All right, so that loss of angular momentum due to gravitational waves is time derivative ji with respect to t. So this ji is my angular momentum vector, and that's going to be equal to the limit as r goes to infinity of r squared over 16 pi, the integral of the real part of, I'll define this capital H in just a second, H star complex conjugate times J hat I, which is an operator operating on this H, integrated over solid angle. And capital H is defined as H plus minus I, the square root of -1, times H cross. And so then this operator, I'm going to specialize to Cartesian coordinates now. This operator J hat in the x direction is going to be minus sine of phi partial with respect to theta minus cosine of phi all times cotangent theta d phi plus 2I the cosecant of theta. That's the x. J hat in the y is going to be equal to cosine of phi partial with respect to theta minus sine of phi all times the cotangent of theta partial with respect to phi plus 2I cosecant theta. And then the z direction is pretty easy. For this operator, it's just d phi, partial with respect to phi. So that's how you would go about computing this. But let's write this down in a simpler way. So that's complete generality. So no assumptions there about symmetries or even coordinates. I mean, I've selected Cartesian coordinates here to express this operator. If we align, say we align Ji with the z-axis. All right, so we've got the spin aligned with the z-axis. That makes this a bit simpler to deal with. In that case, we only have the one component of the angular momentum, just Jz. I feel like there's a good joke in there somewhere. Oh, but I don't have one right now. Limit is r goes to infinity of r squared over 16 pi integral of the time average of the partial with respect to time of h plus partial with respect to phi of h plus partial with respect to time of h cross partial with respect to phi of h cross, close bracket, integrate over solid angle. So that's a much simpler expression if we specialize to Cartesian coordinates and align the angular momentum with the z-axis and express things in terms of our polarization amplitudes here. That's what you get. No more complex conjugation necessary. Then going further, we can do the quadrupole approximation for the loss of angular momentum. And that gives me dji dt is equal to minus 2/5 Levi-Civita ijk all times the average of curly I double dot jm curly I triple dot k upstairs downstairs m time average over a few wavelengths. So a somewhat even easier expression when we take and we re-express this integral in terms of the quadrupole moment. And note that this is a double dot and that is a triple dot. So a second derivative and a third derivative. Can I keep that on board? I've already, rewrite it. Let's do an example. Okay, so I mean, you guys immediately see the implications here, right? So a system that is radiating gravitational waves is losing energy, but it's also losing angular momentum if it had any to begin with. And a system that we know radiates gravitational waves is a binary system. So if it's losing angular momentum, what happens to a binary star system that's orbiting if it loses angular momentum? It spirals, right? It's losing that energy in the orbit. It's also losing that angular momentum in the orbit. And so the binary gets tighter. So let's explore what happens in the particular case of a binary star. And so let's say that we've got, I'm going to draw this marker. Serves me well. All right, let's say we've got some mass, draw bigger, some mass M2, and they're separated from each other by some distance r, and they are in orbit. And let's say that it's a circular orbit going around each other like that. All right? They don't necessarily have to be equal mass. We might make them equal mass, but they are simply two binary stars in orbit separated by some distance, capital R. All right, so I'll spare you the details of this, but I think you could actually write this down very easily to compute the quadrupole moments of a system like this. The integration is very easy, right? They're point masses. So in the center of mass frame, of course, if they're equal mass, the center of mass is located directly between them. But in the center of mass frame, allowing for unequal mass binaries, the reduced quadrupole moment takes the form as follows. So let's see. So curly I, ij, is equal to 1/2 mu, which I'll define in just a second, r squared, all times the following. So I'm going to write the matrix out. Cosine 2 omega t plus 1/3 sine of 2 omega t, 0, sine of 2 omega t minus cosine 2 omega t plus 1/3, 0, 0, 0. Let's see if I can remember this last one. Minus 2/3, I think. Turn the page. Yahtzee. All right. So there's our reduced quadrupole moment for this simple geometry. Here, omega is not a solid angle. It is the orbital angular velocity. Angular. Mu, which is defined to be m1, m2 divided by m1 plus m2, is the reduced mass of the binary. And then R is just the binary separation. I already said that. Like that. Okay, so we've got our reduced quadrupole moment. We can start computing various interesting things about this system. For instance, the gravitational waves emitted. For some observer at some distance, so let's say for observer at R and angle theta, and this is, I'm going to say, with respect to the orbital plane. All right, so that, you know, if we're looking at the board is the orbital plane, theta is this angle. So you all are at theta equals pi over 2. All right, you're, spoiler alert, you're not going to see any gravitational waves. Sorry. Okay, so in that case, we can write down our H plus and H cross from the formulas that we had up before. So H plus is going to be equal to minus 2 over R, omega squared, mu R squared. Again, this is just taking these reduced quadrupole moments and plugging them into the formulas that we had before. 1 plus cosine squared theta, cosine of 2 omega t minus R, and H cross is going to be equal to minus 4 over R, omega squared mu R squared, cosine of theta sine of 2 omega times t minus r. Plugging in my distance there, all right? So looking at this, you can see that the peak magnitude is going to be when theta equals 0, right? So you all are at theta equals pi, and so these go to nothing, right? And so let's take the peak magnitude to get some scaling. Theta equals 0, which is in the plane of the orbit. We get h, just both of them are going to be the same if you work this out. The sort of peak amplitude, characteristic amplitude of the gravitational waves are 4 mu omega squared r squared all over the distance r. And then we can use Kepler's law, because this is an orbit, right? They're a gravitationally bound system. And so Kepler's law, which is just really an expression of angular momentum conservation, applies. We can re-express omega squared, the orbital velocity, in terms of the mass and the separation of the system. It's just m over r cubed. Easy peasy. And that leads to a way to get rid of this r squared, or really anything. Well, not the r squared, but we want to get rid of the omega, right? And so using that, we get the characteristic h is 4 over r, the distance, mu, mass of the system, over r. Hey, did I define capital M? I didn't define capital M, did I? M is just the total mass of the system. Sorry. Yeah, I don't feel like I defined capital M anywhere in here, sorry. Okay. So, let me tell me something strikes you about this. How does the strength of the gravitational wave depend on characteristics of the system or the observer? This is m over r. We often call this the compaction or the compactness of the system. And it goes up with that. More compact systems, which pack more mass into a smaller radius, are louder in gravitational waves. Cool. Another interesting thing in terms of detectability goes like 1 over r. This is unlike other things we try to detect in space, because we're often trying to measure fluxes from things. This is not a flux, this is a strain. Strains go like 1 over r from the source. Fluxes go like 1 over r squared. And so there's a much steeper dependence on flux-based detection methods for things like this. So here, we're trying to measure a strain that goes like 1 over r. That helps in increasing the detection volume, right? Because the intensity, the amplitude falls off more slowly with radius than a flux would, which is kind of cool about gravitational waves, which is kind of cool. Okay. But wait, there's more. I'm actually going to start writing over here now. We can compute the energy loss of the system as well. What's my time look like? I'm going to write this down just because I did it in my notes and it's a good example. So to compute energy loss, as well as the angular momentum loss, what do we need? Looking at your notes, what do I need to compute to calculate dE dt or dJ dt? The derivatives of the time derivatives of mass quadrupole moment. Well, that's easy. I mean, you guys can do this in your head, right? It's just, well, okay. So I had to look it up because I can never remember where the darn minus sign is when I'm taking derivatives, cosine and sine. I've heard all kinds of mnemonic devices about it, you know. But I can never remember. But once you remember where that minus sign goes, you can compute derivatives of sines and cosines all day long. So let's just do the second time derivative. So squiggly I double dot ij is going to be equal to 1/2 mu r squared, all that stays the same out front. And then inside here, the top one, taking 2 time derivatives of that, we've got this is just a prefactor, all right? So this comes out twice. Yeah, question?
Yeah, would R be constant?
We're taking an instantaneous time derivative. So no, over the evolution of the binary system, it will not be constant because you are losing angular momentum. But here we're doing instantaneous time derivatives to compute the instantaneous rates. But if you actually wanted to integrate it and follow the evolution, you would have to account for the time evolution of R because it does change. Very good point. Okay, so yes, I'm going to assume that this is instantaneous and I'm going to keep this constant. All right, so we take out the 2 omega twice, so I get a minus 4 omega squared here, and this is cosine 2 theta t. Great. The second term there, I'm going to differentiate that twice. It's also going to have a minus sign, 4 omega minus 4 omega squared sine of 2 theta t. This is still 0. Same term here, minus 4 omega squared sine of 2 omega t. This term here becomes the same, right? But now, because I had a minus sign here, I get to flip the minus sign here. And I get 4 omega squared cosine of 2 omega t, 0, 0, 0, 0. Because the time derivative of a constant turns out is 0. Okay, boom, derivative. Do it again, you get the triple dot. I've got it in the notes. Okay. So now, I should have written down the triple dot because that's what you get for the energy loss. But you know what this is, right? So once you go to the triple dot, the sign doesn't change. You got to go to the 4th time derivative to get the sign change. But what you do get is you get to bring out another power of this. So this becomes 8 omega cubed, and then you flip this to a sine rather than a cosine. So that's triple dot. It's in your head. Okay, so the energy loss is then d dt, which is our gravitational wave luminosity. We wrote this down for the quadrupole approximation. Curly I, triple dot, ij, inner product, triple dot, curly I, triple dot, ij, like that. Okay, and so now, plugging this all in, this is equal to, just reading off my components from up there, I got the minus 1 over 5, 1 over 4, and remember those are 8s and omega cubes, and flip the sines and cosines to get the 3rd derivative. Mu squared r to the 4th, because, right, I gotta square this thing because I'm multiplying them together. And then some suitable time average of the following: 64 times omega to the 6th sine squared 2 omega t plus 64 omega to the 6th cosine squared 2 omega t plus 64 omega to the 6th cosine squared 2 omega t plus 64 omega to the 6th sine squared 2 omega t time average, right? You see that? Remember, 3rd derivatives in your head. All of that reduces then to minus 1 over 20 mu squared r to the 4th, time average of 128 omega to the 6th. Well, that doesn't, we're assuming over several wavelengths of the gravitational wave, omega is not changing very much. That's our assumption, and so that time average just goes away, right? Does that make sense? And so then dividing this through and simplifying, minus, 32. Hey, Jen, can you see this? Yeah, that's what I thought. Sorry.
I can see it to mu squared.
Okay, mu squared r to the 4th, omega to the 6th. Better?
Yes.
All right, so that's our energy loss rate. Goes like the reduced mass squared. Their separation, very high-powered separation, right, are the fourth. But then also it goes like the angular speed to the sixth. As the binary evolves, what happens to R and omega? So now, Halvard, let's let R evolve as a result of this loss of energy and angular momentum. What happens to capital R? R goes down. Omega goes up, right? And since omega goes up faster than R goes down, as you evolve forward in time, you lose more and more energy to the gravitational waves, right? And that's what happens in the end spiral. It's an instability, right? It doesn't reach an equilibrium. It goes and they merge. Okay, let's do the loss in angular momentum. There's a similar procedure, right? You just plug in the formula that we had before for dj dt in the quadrupole approximation. I won't make you watch me write out all those terms again and do simple algebra on the board. But what you get, again, for a binary with its orbital angular momentum aligned in the z direction like so, you get for the angular momentum loss the following. djz dt is equal to minus 2/5 Levi-Civita ijk of, I'm just writing this down to remind you what the formula is, jm double, that's the double dot, this is the triple dot, km, sorry, it's a vector, km, like that. Plugging all of the various factors in for this and for this, summing as appropriate, and ending up with just the one term I care about. Oh, sorry. On the Levi-Civita, someone should have stopped me, z jk, because I'm limiting it to just that component that we care about, right? Which is the only component that's non-zero in this case. Minus 32 over 5, mu squared, r to the fourth, omega to the fifth. Right, and you can guess where that comes from because we're using a second time derivative here along with the third time derivative. And so combining these things together, I only get omega to the fifth there. Different prefactor. So this thing continues to lose energy. The orbits shrink and they inspiral, given enough time. Right? And essentially this rate. So all of this leads to in spiral. Frequency of gravitational waves. So if you were to go out and measure what the frequency of these gravitational waves are, it is twice the orbital period. So for every passage of the binary completely around 2 pi, you have 2 wavelengths of gravitational waves. So it's twice the orbital period. An interesting thing about this is that if you compare the formula for the loss in angular momentum to the loss for energy right there, we get this relationship. And it is that the loss in energy is equal to the orbital angular velocity times the loss in J. That is only true for circular orbits. If you go and look up your orbital mechanics, that relationship holds only for circular orbits. And so since we didn't say anything special about when we are computing this derivative during the orbit or during the in-spiral, it means that during an in-spiral, the orbits remain circular. And if they start out asymmetric, they will circularize. I didn't compute that for you, but it is true. Okay. So that's application to binary system. Questions?
We're only looking at the quadrupole moments, just not that I want any pretty details, but if you looked at octupole, would those go as 1 over r squared for the string?
I don't know off the top of my head. Yes. There is octopole contribution. Quadrupole is the strongest.
I'm just wondering how it falls off.
I don't know.
There we go.
Yeah. I don't know. So let me think about it for a second and see if I can rationalize it out. So what I'm cogitating on is whether or not it's the power of this R that increases or simply the power of this R that increases for the octave. No. No, that wouldn't make sense.
As you get further away, it looks more and more like just a single
Yeah, a single thing.
lower,
Yeah.
lower pole.
A lower multipole. Yeah. That would make sense, actually. And the quadrupole moment is appropriate in the limit. I've erased all my limits of R going to infinity. So maybe it is true that the higher order moments fall off faster with distance from the source. I haven't thought about that. Let's say sure. All right, good question. All right, so let's talk about some other sources of gravitational waves. I think I'm going to go ahead and put something on the board. Oh, there goes my notes. And it like erased the one thing that I actually wanted to keep, but that's fine. That's fine. Let's see if we can do this. Okay, so we just talked about binary systems, and the characteristic. Let's see if I can write this down someplace where you all can still see it because it's now covered up by the board. So what we just wrote down in the case of a binary system, it turns out that this is fairly true for most systems. So the characteristic amplitude of the metric perturbation, or the gravitational wave strain, is that we had this 4 over R, mu, the reduced mass, total mass of the system, divided by the separation of the system. So for some binary, plugging in some numbers that are relevant, we're talking about 5 times 10 to the minus 20 time, for a source at a distance of 1 megaparsec. For a source that has a total mass of 1 solar mass, times its compaction. So whatever this compaction happens to be, 1 is pretty compact, right? So the point here is that this prefactor is darn small. And so you're talking about, for typical sources, very, very small strains. And so this is hard to detect, naturally. And if you were to guess at what the characteristic frequency might be, you can use Kepler's third law to eliminate some of the things, but you can also use the frequency must go something like the inverse of the dynamical time. Characteristic frequency of the waves. That look familiar, Mike? Yeah, Mike put that in a paper. Which goes something like the square root of the density of the system. But plugging in either this for a system that's not necessarily a binary, or using Kepler's relationships for a binary system, you can get a typical characteristic frequency of the gravitational waves, which is something like 1 over the total mass of the system, the compaction of the system to the 3/2 power, which that's that. You can get that from either this, which you can just look at this and go, oh yeah, that's rho, square root of rho, or from Kepler's laws. So we're talking about frequencies here of 2 times 10 to the 5 hertz times the inverse of the mass of the system in solar masses, all times the compaction of the system to the 3/2. That's a characteristic frequency for a gravitational wave from some source characterized by these things. Right? And so it's going to go down with mass, up with compaction, like that. All right, let's see if I can put this on the screen. Wish me luck. I'm doing this from my iPad, so 50-50. Eh? Eh? No. Anything? You got nothing, huh? That's great. All right, I'm gonna have to use my laptop. That's fine. Just want to show you this picture. See anything? Groovy. There we go. All right, cool. Okay, so now taking that frequency and plugging in some typical systems that we're interested in and characteristic values for compactness and the total mass of the system, we get a gravitational wave spectrum, right? And it's much like the electromagnetic spectrum where you have all these sources emitting across different bands in the spectrum. Of course, and then down here we have different ways of detecting gravitational waves at those different frequencies. The things that we're most interested in are on the high side, the high frequency end here. And so compact binaries in our galaxy and beyond, things like compact neutron star systems, neutron star binaries, black hole binaries, they span this range in frequency from 1,000 hertz down to 10 to the minus 3-ish hertz, right? And you can see where that comes from because these systems harden, right? As the radius goes down, their mass doesn't change, but the frequency shifts to higher and higher frequency, right? 2 times the orbital period. Down it goes. So this is kind of the high frequency end, and this is where terrestrial interferometers like LIGO work best, in that high frequency range. You also get things like supernovae and rotating neutron stars here. In this high frequency range, they happen to more or less overlap with this bandpass, not as much on the low frequency side. These stellar, single star kind of objects tend to be on the higher sensitivity. But LIGO's sensitivity detect peaks around 100 hertz in this gravitational wave spectrum. And then as we push the lower frequency, you actually go up in mass in some sense. Just looking at that equation, you can understand why that is, right? You go up in mass, you get that 1 over m there. You're going to lower frequencies. And so this is the realm of space interferometers like LISA, which is like LIGO in space, only bigger, right? And here you have things like supermassive black holes and supermassive black hole binary systems. And so this is a big thing that is a target for detection for things like LISA and space-based interferometers. It's also a target for detection for something called pulsar timing arrays, which are very cool. These are radio efforts where you use pulsars like really super accurate clocks, and by measuring how their timing changes, like all the pulsars in the galaxy, right? You string them all together like a big array of clocks, and then you can measure the passage of gravitational waves by how their periods are changed. Like really, really, really small changes, right? Cool stuff. But that's pretty low frequency gravitational waves is what you can detect with that. The high frequency stuff is those loss. And then as we're pushing to even lower frequency, quantum fluctuations in the early universe leave an imprint on the cosmic microwave background radiation because of gravitational waves induced from those fluctuations. Those are very low frequency, at least now. And so there's efforts to try to detect that in the cosmic microwave background radiation. And so there's this entire range of objects that emit at different frequencies in the gravitational wave spectrum, which is very cool. Now, I think it's kind of fun, and I hope you've read the book. I hope you read the chapter on gravitational waves. It's a quick read, and I'm not going to talk about everything that's in that chapter. But it's really cool already to be reading a book that was written before gravitational waves were detected. And it's all aspirational, like, oh, we might be able to detect this, or LIGO will be able to see this or that. And now it's like, we're detecting these things one a week. There was another detection of a black hole binary on Friday by LIGO. So that's 2 so far in 2 weeks, going on 3 now, operating in 03. It's become a routine. It's incredible to me, right? And so to read the book, and they're talking about this is going to be very important. In order to do this, when we actually are able to detect gravitational waves, we have to do this, that, and this. And now here we are. We're doing this. So I think that's very cool. Okay, so I thought that was a nice image and better than anything I could draw on the board about the entire gravitational wave spectrum. So that's all I want to show. Questions about that? I'll talk a little bit more about a few other details now on the board of some sources of gravitational waves. That's right.
So when they spiral, at some point
They break that. And the reason that it still works, one, that was actually a great test of the weak field limit of Einstein's equations, and to make sure that as you go to the strong field limit, things don't change drastically. But the reason it still works is that where we are detecting the waves, are in a weak field. Does that make sense?
They're still non-linear waves, right?
Absolutely, absolutely. And so before LIGO detected gravitational waves, it was an open question of whether or not this would not change things drastically, such that our weak field approximations were incorrect. Now, when we create gravitational waveforms for things like binary black hole mergers, we typically don't use the quadrupole formula to extract the gravitational waveforms. And that's what the second half of the chapter on gravitational waves is about, is how to accurately extract gravitational waves without making the quadrupole approximation. And those are the approaches that are actually used when we do template matching to find gravitational waves in LIGO. Yeah, we still do that for supernovae, the quadrupole formula. But we could, in principle, for fully relativistic calculations, do exact extraction of the gravitational waves. But that's absolutely right. But there's not a huge difference, it turns out, from the weak field limit. But it is the strong field limit. And so some of these things do break down, especially for black hole mergers. Supernovae, up till the point of black hole formation, are still essentially in the weak field limit, relatively speaking. So a neutron star is a relativistic object, for sure, but it's kind of well described even by the weak field limit of GR. And so that's another reason why the quadrupole formula for supernovae, at least, probably aren't that different from the full extraction.
Not for supernovae, how close would LIGO's current created so they have to actually be before we could hopefully try and detect something from them? Because the amplitude's gonna be a lot weaker.
What distance do we always say?
Could be galactic, so 10 kiloparsecs.
10 kiloparsecs, because it's a nice round number. And that's not just galactic, that's practically our end of the galaxy. Now, if you look at the details of the calculations, we could push that to tens of kiloparsecs. But
how many light years in a
a parsec is 2.2 light years, right? Jesus Christ. I'm not an astronomer.
There's like 3,200 light years.
Like, so many Earth seconds. So.
Wait, so it's 3.2 light years in a parsec.
Yeah.
Okay. There's a Google.
Yeah.
How many? Okay, so there you go. So pretty close. But I think we are working on how to push that detection threshold out further and further. And the things that go into that are good modeling, as well as good techniques for extracting the signal from the data. And so one of the reasons that binary black holes work so well in terms of detection is that we have very good numerical relativity models of this stuff, right? Where we actually do the exact extractions using the formulae and the methods that are in the book. And so we have waveforms that can be used as what's called template. And then you do something called match filtered analysis, where you get some data stream. I should have left my laptop plugged in. I could have brought this up from LIGO, which is just strain as a function of time. And you take that template and you just slide it over the data and see if anything hits, right? If anything lines up with that in terms of an excess of power. And so you can do this template matching, this match filtered analysis, to really pick out from the high noise data a signal. You can't do that with supernovae because most of the signal from supernovae is stochastic, right? We don't have a clean signal, right? A binary black hole produces, if given the parameters of binary black hole system, it produces a precise waveform as it inspirals in the absence of matter. But supernovae aren't like that. The signal is stochastic, and so it's a bit random. And so you can't do that same match filtered analysis. And so you're limited to just looking for excesses of power. But we are working towards trying to understand good ways to search for supernovae in the signal so that we can push the detection thresholds. As a matter of fact, this week, a few people from the LIGO supernova group who are actually working on trying to find supernovae in LIGO data are visiting here Wednesday through Friday to work with us on trying to get input from theory on how to optimize searches for supernovae in gravitational waves. They're very optimistic and very enthusiastic. And it could be possible to even push out to maybe stretching the megaparsec limit with advanced LIGO if we have really good input data from the theory side of things and we understand the signal. And that's the thing. With a compact binaries, we understand the signal. It's very well modeled and very well quantified what the signal from a compact binary merger is. And now it's measured. That's not so true for supernovae for a lot of reasons. One, the stochasticity, but two, there's an enormous range in parameters. Every star is different, right? Every star that collapses to make a neutron star is a little different, right? Different spin, different mass, different metallicity, if that matters. Different history of mass loss and binarity, and all these other things that go in that can affect very directly the gravitational wave signal. And so the parameter space is huge and multidimensional. And so it's not well covered. That's one problem, on top of the stochasticity, which prevents us from doing this match filtered analysis kind of thing. So the goal is to come up with better ways to look for supernovae so that we can push the distance at which we could detect one. And the cool thing is, if we figure out this is something that we can do a posteriori, right? Because if we figure out good ways of doing this, all the data still exists from LIGO. We can go back in time and look for supernovae again in the past observing runs from LIGO if we come up with good theory input and statistical methods to look for those signals. So there could be a supernova in the data. Could be. All right. One thing that you'll see, let's see here. We talked a little bit about the high frequency side of things. I'll just talk about this because you'll hear this when people are talking about compact binary mergers. And this is an important parameter that's oft quoted when it comes to some of these things. Another important point about modeling these waveforms for compact binary mergers or supernovae or whatever, they're actually, that input from numerical relativity is critical to extracting physical information about the system. It is entirely possible that LIGO would have detected all of the binary black holes that it has detected so far, right? Because they're excess of power, you get this very bursty signal, it does this characteristic chirp, it's in the data, right? And some of them are very high signal noise, so they're there. But LIGO wouldn't be able to tell us the mass of the system, right? What's the likely probable mass of the two black holes, right? What's their likely orbital spins, right? Their actual spins of the black holes, right? et cetera, et cetera, et cetera. All these other physical parameters of the systems that we care about are because we can model the waveform, right? And we do this for an enormous range of conditions of binary black holes. I remember the people who were doing it at LIGO, at Caltech while I was there. They were frantically working, this was right before 01, they were frantically working to cover the parameter space of binary black hole mergers so that the templates were there to be used for the searches when 01 turned on. I don't think they slept. And they produced reams and reams and terabytes of data working on these things. Okay, so one thing you'll often hear quoted, oh, this is a new marker? You're coming home with me. Chirp mass. The chirp mass, which I'll write just as a cursive M. This looks a lot like the reduced, oh, that's not an I, that's a 1. M1, M2 to the 3/5 divided by M1 plus M2 all to the 1/5. So that looks a lot like the reduced mass, but with some funny powers. And this characterizes the orbital evolution of the binary, and let me show you how. You can write down a differential equation for the evolution of the gravitational wave frequency. This goes actually sort of to Halvard's question. So if you go back to our derivations here, and then you turn this around to compute the time derivative of f, including these orbital well, I erased the equations now. Oh, it's over here. Right? So turn this around, solve for the orbital evolution, and calculate the time rate of change of the frequency in gravitational waves as a result of the binary hardening as you radiate gravitational wave energy. I'm not going to do the derivation, but what you get is the following differential equations. F df dt is equal to 96 over 5 pi to the 8/3, the chirp mass to the 5/3, and the frequency, sorry, to the 11/3. And this is to leading order. This is an expansion, okay? And so this chirp mass describes how quickly the frequency is changing. Frequency is going up, okay? Which is why it's called a chirp mass, because these things make a characteristic chirp when they merge. And go, that's not a bad impersonation, actually, what it sounds like. That might have contracted a little fast. What was the chirp mass? So the point being is that if you detect a gravitational wave signal, you can measure its frequency, but not only that, you can measure the time rate of change of its frequency directly from the data, which gives you this chirp mass, which gives you some constraint on the total mass and the reduced mass of the system. Now, this is another reason why they say they don't directly measure the mass of these binary systems. LIGO measures the chirp mass, because that's what they're measuring from the frequency and the rate of change of the frequency. And so that's the thing they have the tightest constraint on, because that's directly measured. Now, you fold these things into a numerical relativity calculation, you can back out the individual masses of the system from all of this, right? And of course, you can just turn this around and say that the mass is 5/96 pi to the minus 8/3. I'm just inverting this equation. F to the 11/3, the minus 11/3 times F dot, the time derivative to the 3/5, right? If I just turn this around to solve for chirp mass. And so these two things are directly measurable by LIGO, for instance. And so then you can get that chirp mass. And that puts a constraint on the total mass of the system, like that. I've got nothing else to write on the board, but what other questions do you have? We've got 5 minutes, we can keep talking about sources of gravitational waves. Supernovae, they're not as loud. They typically do not produce a chirp either, because that chirp that we're talking about is coming from this increase in the frequency due to the end spiral, right? And so you get this very characteristic, let's draw some on the board, right? where it looks sinusoidal. The amplitude starts to go up. It's kind of rough, right? Oh, let's just do this. Okay, and so for a binary in spiral, this is a very rough artist's impression of the frequency evolution. So out here, the amplitudes are small, the strains are small, right? The frequency gets larger, and the amplitudes start to go up as well. Again, we're just doing this in time until you get this merger, and this is, let's say, a black hole merger, right? And so when the event horizons actually merge, it's very loud. And then after that, so merger is here, but the gravitational waves don't stop there. The space-time is still quite perturbed. And it takes time for it to radiate that perturbation away, radiate the energy contained represented by that perturbation away. And so this period here is called ring down. And so the new, very massive black hole rings down. In this process, I should have computed this. These are great order of magnitude things that we could have done just from what we had on the board. But for a given binary, I could have done it with that binary example I gave you next time. Solar masses of energy are radiated, depending on the mass of the system, right? So several solar masses of energy are radiated away in gravitational waves. So the gravitational mass of this system is reduced, right? Like the first binary black hole merger, there were like 230 solar mass black holes, right? So 60-something masses of gravitational mass initially, but they radiated away, I can't remember, it was 3 solar masses of gravitational energy, reducing the mass of the final black hole by that much, right? And so there's an enormous amount of energy that gets radiated. I mean, we're detecting these things at 100, 150 megaparsecs. So I think for O3, for LIGO, the neutron star merger distance threshold is like 150 megaparsecs. That's way out there. I mean, I think it's way out there. So it's kind of cool. Other questions?
How close would you have to be to the black hole, or how far away would you have to be, like assuming you were shielded from all the electromagnetic radiation, to be killed by just the gravitational waves?
So this is another fun back of the envelope thing, and let's see. So the strain is the thing that we care about most, right? And so so let's do this. Okay. So let's assume that this is our strain. We've got a 1 solar mass system. Its compactness is 1. All right. And so the strain, remember, this H is delta XC over XC. That's a strain, right? And so let's say you are 2 meters tall. You're not, but let's say it's an easy number. Okay, so we can plug this in and calculate this inversely to tell me at what point do I start to feel that. How much, if I were to stretch you, Aditya, bolt your feet to the floor and just start stretching you like in the medieval days, at what distance do you think you'd start to feel it and be uncomfortable?
Not very large.
A factor of 2? Yeah. Wow. I mean, I'd feel it at like a centimeter, right? I'd certainly feel it by a few centimeters, right? So what is that? Let's say it's a centimeter. Let's say that you don't like to be stretched. A centimeter is not that far, but if I were stretched a centimeter, I'd feel it, right? I'd start to feel it at that point. That's about what? 1%, right? So 1%, let's call, right? So that's what we're looking for, 0.01. Okay, so someone back this out for me. Who's got a calculator? Let's take this megaparsecs down to the point where, let's solve for R such that this is equal to 1%. But I need to factor in the megaparsec, right? So I need to take R over here, I need to put 0.01 here, and then I need to put in megaparsecs in units of meters or something. I don't care. Someone calculate that for me. I don't have a calculator. I obviously don't know how many megaparsecs are in a centimeter or a meter. I don't know that.
Meter.
All right. You all better do this faster than me.
Still trying to connect the internet.
Okay.
There's
1.
10⁻². meters of it.
Okay. So then divide that by. Oh, that is not. Come on, Google. and then multiply through by 5 times 10 to the 20. So
Factor 4.
yeah, that sounds right. Yeah.
150.
Yeah.
That's all right.
So that sounds right. 150 kilometers?
That's accurate.
150 kilometers. For, you know, a typical one solar mass, fairly compact thing. So like a neutron star that was emitting gravitational waves, or, you know, a supernova even, roughly that.
Now, could you safely be at that distance without being pulled?
Depends on the object, right? If it were a binary, compact binary, you might be able to get within 150 kilometers. Of course, it'd be pumping out the gravitational waves probably even louder than this. But yeah, okay, so 150 kilometers. That's fun. All right, other questions? Any other back of the envelope things we can do?